In this lesson, we're going to look at models for exponential growth and decay. We'll start off with a model for population growth. We'll get exponential growth when the rate of change is proportional to the population at the time. That leads to this equation where we have the change in population over the change in time, which gives us the rate of change in population is some constant r times the population at the time, and the r is the constant rate of growth. Then the population can be modelled as p is equal to p naught, the initial population, times e to the rt. We'll see after we've studied some calculus how we can obtain this equation from the given equation that we started off with. And when the population is increasing, then the r is positive. When the population is decreasing, r is negative. We'll use the population model to solve this problem. In the year 2000, the population was 6.1 billion, and the estimated growth rate was 1.4% per annum. If the population continues to grow at this rate, when will it reach 122 billion? So the solution is to use the population model that we've developed, and we'll set time as 0 in the year 2000. We know that the population is 6.1 billion in the year 2000, that is when t equals 0. And that the rate is 1.4%. So we'll put those two figures into our model so that we get p is equal to 6.1 e to the 0.014t. So using that formula, we want to find t when p is equal to 122 billion. So we'll substitute the 122 for p, and we need to find what t is. Now to get to the t, we need to get rid of the 6.1 firstly, so we'll divide both sides by that, 6.1. And now we have to undo the e to the power of. So we want the inverse function of the e to the power of, and that is the log function, log base e. So we'll take log base e of both sides, and then we'll divide by that 0.014, and then calculate that out on a calculator to get approximately 214 years. So it's 214 years after the year 2000, so the population will reach 122 billion in the year 2214. Radioactive substances decay by emitting radiation, and the rate of decay is proportional to the remaining mass. So once again, we have a situation where the change in mass divided by the change of time is some constant times the remaining amount, mass in this case. The r is positive, and by putting a negative in front of that, then that means that constant is a negative amount representing decay. So we can use the exponential model once again, where the mass is equal to m naught, some initial amount, times the exponential function e to the negative rt. The half-life of a substance is the time required for half of the mass to decay. In this example, polonium-210 has a half-life of 140 days. How much of a 300 gram sample remains after 1 year? And how long does it take for the sample to decay to 200 grams? So we'll use that exponential model, m equals m naught e to the negative rt, and we're given that initially we have 300 grams, so our m naught is 300. We can put that value into the equation. However, we're not told what r is, so we need to work that out. And we can work that out from the half-life. The half-life means that half of our sample of 300 grams, which is of course 150 grams, that much is left at 140 days. So then we can plug those two values into the equation. So our m is 150 and our t is 140. We are trying to find r, so we have to get to the r. We'll divide both sides by the 300 firstly. We have to undo the e to the power of, so that means we take log of both sides, and then we can divide by negative 140 to get our r as approximately equal to 004951. And we need to keep that value in our calculator so that we can use it later on. And so our equation then becomes as shown there, with our r and m naught in the equation. We're now asked to figure out what the mass is after 1 year. Now 1 year, of course, is 365 days. We must use the same unit there, days. And so we'll put our 365 in for t and then calculate that out. We'll get 49.26 grams. In the second instance, we want to find t when our mass is 200 grams. So we'll put the 200 in for m. We'll use the equation that we've worked out. And now we're trying to find t. So once again, we'll divide both sides by 300 firstly. And then we'll undo the e to the power of by taking the natural log of both sides. Getting t by itself. We'll work that out on our calculator to get 81.9 days. We have developed exponential models in this lesson, for example, for population growth given by that exponential equation, and also for radioactive decay as given by that equation, where in the second case there, our rate is negative.